Hello, men and women of science. This is Mr. Cochran here to talk about solubility. In this podcast episode, we'll be discussing the effect of temperature on the amount of solute one can dissolve in solution, and also we'll do a short explanation of how to calculate amounts that can be dissolved using solubility graphs. Now, the first thing we're going to be looking at here is a graph of solubility. The vertical axis of the graph represents the grams of solute particles that can be dissolved in 100 grams of water, and the horizontal axis shows the temperature in degrees Celsius. One of the things you'll notice is that most of the lines slope upwards, with one of the lines actually sloping downwards. This means that as temperature increases, the solubility of most solute particles will also increase, but there are exceptions. These lines that you see on the graph represent saturation levels. For example, you can see on the graph that at 10 degrees Celsius you can dissolve approximately 30 grams of potassium chloride, whereas at 70 degrees Celsius we can dissolve approximately 50 grams, a little bit less, about 48 grams. These values represent the saturation levels at the given temperatures. We would describe a solution where only 30 grams of potassium chloride were dissolved at 70 degrees Celsius, an unsaturated solution. What would you call a solution where you had 60 grams of potassium chloride in solution at 70 degrees Celsius? If you said super saturated, you'd be correct. Now, the slopes of the lines also give us clues as to how much temperature affects the solubility of a substance. You can see here that calcium chloride is strongly affected by increases in temperatures. You can tell this by the steep slope of the line for calcium chloride. Sodium chloride, on the other hand, has a relatively flat line. That means that the solubility of sodium chloride is not affected greatly by increases in temperature. Now let's take a moment and examine potassium chlorate. You can see that the line for potassium chlorate arcs upwards as the temperature increases. At 90 degrees Celsius, we can dissolve roughly 40 grams of potassium chlorate. At 30 degrees Celsius, we can dissolve roughly 10 grams of potassium chlorate. This means that a 60 degrees Celsius temperature change from 30 degrees to 90 degrees results in a 30-gram increase in the amount of solute particles you can dissolve for potassium chlorate. Conversely, then, if we were to cool a saturated solution of potassium chlorate from 90 degrees to 30 degrees, you would expect 30 grams of potassium chlorate solid to precipitate out of every 100 grams of water. Speaking of potassium chlorate, let's take a moment and do a practice calculation with potassium chlorate, where we're going to look at how much potassium chlorate would we expect to be able to dissolve at 30 degrees Celsius, for example, in different amounts of solution. You can see from the graph that 10 grams of potassium chlorate can dissolve in 100 grams of water. This gives us a ratio of 10 grams of potassium chlorate per 100 grams of water. But how many grams of potassium chlorate would we be able to dissolve in, say, 350 grams of water? You can see that these types of problems can be easily solved by setting them up as equal proportions. If 10 grams of potassium chlorate dissolve in 100 grams of water, then how many grams dissolve in 350 grams of water? If we multiply both sides of the equation by 350 grams of water, you see we get the following equation. Notice how grams of water factor out. And our resulting answer is 35 grams of potassium chlorate. Now, these are nice round numbers, but this method works very well even when the numbers aren't so convenient. Well, I hope you found this brief discussion of solubility helpful. This is Mr. Cochran, signing off.
Intro and exit music was Not My Slave and Goodbye Goodbye by Oingo Boingo. Solubility graph provided by Chemistry, Matter, and Change from Glencoe Science 2005 edition.
Chemistry is cool, baby.